In tonight's stream, we're going to look at what is the relationship between position, velocity, and acceleration. And we're going to practice solving these types of problems using differentiation as well as integration. Now, first thing we need to explore is what is that relationship between position, velocity, and acceleration? Let me see if I can reposition myself here. I've got a nice little halo with that light above my head. There we go. That's a little bit better. All right. So when we talk about the relationship between position, velocity, and acceleration, let's first start by saying that we have the function s of t, which is a differentiable function. That's going to be our position function at time t of an object moving along a line. So let's define that. We've got if the differentiable function s of t gives the position at time t of an object moving along a line then, and let's talk about our relationships. So if that's true, if we have the differentiable function s of t that gives the position at time t of an object moving along a line, then we can say the following. We can say that the derivative of our position function, so s prime of t, is going to equal v of t, our velocity. And we can go one step further than that, and we can say that if I take the second derivative of my position function, which would be the first derivative of my velocity function, that I'm going to end up with a of t, which is my acceleration. Okay. So think about if you have position and we take the derivative, we're going to end up with velocity. And if we take the derivative of velocity, we're going to end up with acceleration. All right. Now, let's think about the other direction. If we know that a of t is acceleration, how would we get back to velocity? We would have to take the integral of a of t. So we can say that the integral of a of t dt is equal to v of t plus c. So remember, we've got to remember that constant plus c because this is an indefinite integral. And now going along in that same reverse direction, we could say that the integral of my velocity, v of t dt, would get me back to my position function, s of t plus c. Okay, so we've got these going in both directions for us. Okay, what questions do you have at this point? Any questions just about those generic relationships? No? All right, let's try some problems then. All right, here's our first example. So starting at time t equals 0, a particle moved along a line so that its position at time t seconds is s of t equals t squared minus 6t plus 7. Find its velocity at time t. When is its velocity 0, and when is the particle moving to the right? So we've got a couple different questions we want to answer here, okay? Now first, if we know that s of t is equal to t squared minus 6t plus 7, that's our position function, and we want to get to velocity, we need to take the derivative of our position function. So we're going to have s prime of t equals v of t, which would be 2t minus 6. Okay, so that right there is my velocity function. So find its velocity at time t, check, we've done that. Now it wants to know when is the velocity 0. So we're going to take 2t minus 6 and set it equal to 0. All right, to solve this, we're going to do add 6. And then we are going to have to divide by 2. And we are going to get that t equals 3. Now, it's important that we make sure we include some units here, okay? What units would I need for time here? T equals 3 what? Okay, we need t equals 3 seconds. So when is the velocity 0? The velocity is 0 when t equals 3 seconds. All right, last part of this question asks me, when is the particle moving to the right? Now, the particle is moving to the right when my velocity is positive. Let's make a little note of that. Particle is moving to the right when velocity is positive. Now, this particular question doesn't ask me this, but let's talk about it while we're discussing this topic. If it wanted to know when the particle was moving to the left, we'd look for when the velocity is negative, okay? Now, what I like to do at this point is I like to make myself a quick little number line. Let's label it v of t so we know what that number line is for. And we want to put 3 on our number line. And I'm going to put a little z under there to remind me that 3 is on this number line because it's a 0 for my velocity function. Okay, so we need to test a value less than 3, and we need to test a value greater than 3 so that we can determine when this velocity function is negative and positive. Okay, so why don't we say plug in 2? Okay, if I were to plug in 2, my velocity function, so v of 2, would end up being a negative. Let's plug in a number greater than 3, say 4. Okay, we're plugging 4 into the velocity function, and we're going to find out that 2 times 4 minus 6 is going to give me a positive answer. Okay, keep in mind that the answer itself isn't as important here as much as whether it's negative or whether it's positive. We now know that my velocity is positive when t is greater than 3 seconds. So my particle is moving to the right. Whoops, sorry about that. Particle is moving to the right, so my velocity is greater than 0 when t is greater than 3 seconds. Okay. Can you still see me, Ashley? Can you hear me? See my writing? Any luck there, Ashley? I actually think it's just you and me right now. Okay, perfect, great. Do you need me to go back and redo anything from where it froze, or you caught back up with us? Awesome, great. And it looks like we've got another person that just joined us as well, so welcome. All right, any questions from that first example? No? All right, here's our next one. This time we have the equation of motion of a particle is s equals 2t cubed minus 5t squared plus 3t plus 4, where s is measured in centimeters and t is measured in seconds. Find the acceleration as a function of time, and it also asks what is the acceleration after 2 seconds. So in this case, because we start with position, we're going to need to take the derivative to get velocity, and then we'll take the derivative of velocity to get our acceleration function. So we have that s equals 2t cubed minus 5t squared plus 3t plus 4. Okay, so we're going to take that derivative of our position function, which is going to give me velocity, and that's going to give me a 6t squared minus 10t plus 3. We don't want to stop there, though, because that's just velocity. So now we need to take the derivative of velocity, which is going to give me acceleration, and that's going to give me a 12t minus 10. So right there, we have our acceleration as a function of time. Okay. What do I need to do to now figure out what the acceleration is after 2 seconds? Any ideas on that one? Yeah, perfect. So t equals 2, so I'm going to simply plug that in. So I'm going to get that a of 2 equals 12 times 2 minus 10. So we've got 24 minus 10, which is going to give me 14. Now, here's something important. I need to think about units for acceleration. What are my units going to be in this problem? Centimeters per second squared. Perfect. So keep in mind when we talk about position, we would just have centimeters. If we were talking velocity in this problem, we'd have centimeters per second. And now that we're at acceleration, it's centimeters per second, which is at centimeters per second squared. Good job. So a of 2 is going to equal 14 centimeters per second squared. Any questions on that one? We're kind of starting out slow to warm up and make sure we know these relationships, and we'll get a little bit more complicated as we go. Is this a topic that you guys have already covered in your classes? Awesome, good. So you guys are probably cruising right along with me. Perfect. Okay, never hurts to get more practice though. All right, this one says that an object is moving freely in the atmosphere. Perfect. The force of gravity pulls it toward the Earth. Near the surface of the Earth, the acceleration due to gravity is approximately 9.8 meters per second squared. If a firework is fired vertically from the ground at an initial velocity of 40 meters per second, when does it strike the ground? Okay, so a couple things we need to think about in the information they give me. Okay, it tells me that the acceleration due to gravity is approximately 9.8 meters per second squared. Okay, we want to take the positive direction to be up, and since the rocket's actually coming back down to the Earth, we're going to use a negative. Okay, so positive direction's up, coming back down is our negative direction. So we are going to say that our acceleration function, a of t, is equal to negative 9.8. Okay, does that make sense? Okay. All right, now we want to figure out when does it strike the ground. Okay, so first thing we need to do with that a of t is we actually need to integrate it to find our velocity. And then we're going to integrate that to get our position. All right, so let's check out what we got here. If we integrate negative 9.8 dt, we're going to get negative 9.8 t plus a constant, and let's call that constant C1. Okay, we now need to apply our initial condition, which they give me, that says V of 0 is 40. It says right here that it is fired vertically from the ground at an initial velocity of 40 meters per second. Okay, so let's use that. We get that V of t equals negative 9.8 t plus C1, and we know that V of 0 is going to equal negative 9.8 t plus C1, which is now equal to 40 based on our initial condition. So what's that tell me my first constant? Oops, I forgot a 0 in there. Let me go back and fix that. This should be negative 9.8 times 0 plus C1. What's that tell me that first constant's going to equal? What's C1 equal? $40, perfect. Okay, now that we have a fully defined velocity equation, we can integrate our velocity equation to get our position function. So now we need to do the integral of negative 9.8 t plus 40 dt, which is going to equal negative 9.8 t squared over 2 plus 40 t plus that second constant. Okay, now we have another initial condition. It tells me that the firework is fired from the ground. So this initial condition of from the ground tells me that S of 0 equals 0. So if I use that initial condition for my position function, what am I going to find out that the constant is for my position function? So let's think about this. First, we might also want to consider or notice that that negative 9.8 t squared over 2 is actually going to reduce to a negative 4.9 t squared. So if I take my position function, I've got a negative 4.9 t squared plus 40t plus that second constant. And if I plug in 0, so we're looking at S of 0, which equals 0, I'm going to find out, I'm going to try to squeeze it in here in this corner, that that constant for my position function is equal to 0. Okay, that tells me then at this point that my position function is simply negative 4.9 t squared plus 40t. Okay, let me squiggle on up here and then we'll get some more space. Any questions how we got that position function based on moving from the acceleration function to our velocity function, using that initial condition, and then getting our position function and using our initial condition. Okay, now here's the deal. We still haven't technically answered the question. We're so close, though. It wants to know, when does the firework strike the ground? So I need to make sure that I am taking my position function and setting it equal to 0. So when does it strike the ground? We want to find out, when does S of t equal 0? That's what we're trying to determine. Okay, so let me make us some space here. I'm going to clean this up a little bit. We know the following at this point. We know that our A of t is negative 9.8. Our V of t we found was negative 9.8 t squared. Nope, t plus 40. And that our position function is equal to negative 4.9 t squared plus 40 t. All right, and in order for us to answer this question of when does it strike the ground, we need our position function to equal 0. So we need to set negative 4.9 t squared plus 40 t equal to 0. Notice that both of those terms on the left-hand side of this equation have a t, so we can actually factor out a common factor of t. We'd be left with negative 4.9 t plus 40 equals 0. Now, as we solve this equation, remember we need to set each factor equal to 0. So we're going to get t equals 0, and negative 4.9 t plus 40 equals to 0. If we subtract this 40 and then divide by 4.9, negative 4.9, we are going to find that t is approximately 8.16 seconds. Now, notice that when I solved this equation, I also got t equals 0 seconds. But think about what the question's asking. It says, when does it strike the ground? It's going to go up and then come back down and strike the ground at 8.16 seconds. That t equals 0 is just representing that initial condition that at time equals 0, it was on the ground. So that is not going to answer our question. So 8.16 seconds. Okay. Any questions on that one or clarification needed on any parts? Good, good, good. I'm so glad that helps, Ashley. All right, you guys ready for the next example, or you have any other questions on that one? All right, let's do it. Okay, here's our next one. We have a mass on a spring that vibrates horizontally on a smooth, level surface. So you can kind of visualize what's happening over there in the picture. Its equation of motion is x of t equals 20 plus 6 sine t. So we're going to have some trigonometric functions to work with on this one, where t is in seconds and x is in centimeters. First thing we want to find is our velocity at time t. So if we want our velocity, we are going to take the derivative of our position function. So we need x prime of t, which is going to give us our velocity. And we are going to find that the derivative of 20 is 0, so we're not going to write that. And the derivative of 6 sine t is going to give me 6 cosine t. So here is our velocity at time t. So that first part just requires us to take the derivative. Now, the second part says, find the time at which the mass changes directions. So it's important to know that the mass, our weight, or on our spring, that mass on our spring is going to change directions when my velocity equals 0. Okay, so I need to take that answer I got in the first part, 6 cosine of t, and I need to set it equal to 0. Okay. Now, as I go through and I solve this, if I divide both sides by 6, I'm still going to get 0. So I'm really looking for when does cosine t equal 0. Any ideas on when cosine equals 0? So when my time is 0, my cosine is 1. I think you're thinking about this a little bit backwards. So we want to figure out what angle would make cosine 0. So a couple ways you can kind of think about this. If you no, it's okay to think about the unit circle. So if you think about the unit circle, okay, cosine is going to equal 0 at pi over 2, 3 pi over 2, 5 pi over 2, so on and so on. Does that make sense? Awesome. Good. The other thing that you can think of is, I personally think back to the graph of cosine a lot. So I know that this is pi over 2, and this is 3 pi over 2. And I know that this cosine graph would just continue on, okay? So when we solve this, we're going to find that this happens at pi over 2, but it then continues to happen every additional pi from there. So we're going to have to generalize this as plus n pi, okay? Where n equals 1, 2, 3, so on and so on. So that n pi is going to give us pi over 2 plus pi, which is 3 pi. Pi over 2 plus 2 pi, which is going to give us that 5 pi over 2. So it's going to give us all those multiples. Okay. Yeah, so that was our answer, actually. We kind of just started talking about it, but we've got our answer. So find the time at which the mass changes direction. It's going to change direction at every pi over 2 plus n pi, where n is 1, 2, 3, ... Okay. All right, now the last part says, in what direction is the mass moving at times t equals pi seconds? Okay, so keep in mind that if my velocity, so v of t is greater than 0, if it's positive, that means my mass is moving to the right. If my velocity is less than 0, if it's negative, it means it's moving to the left. Okay, so we need to determine whether velocity is positive or negative at pi seconds in order to decide whether it's moving to the right or to the left. So let's find out what v of pi equals. So we're going back to that velocity equation, but we're going to plug in pi. So we need 6 cosine of pi. Cosine of pi is actually equal to -1. So we're going to get 6 times -1, which would be -6. And keep in mind, this is velocity. So really it would be -6 centimeters per second. But what's important to us here, because we're trying to answer whether this mass is moving left or right is that this is a negative 6. So because it's a negative 6, we know that this is moving to the left. Boom. What questions do you have on that one? I do want to go ahead and make a comment on this slide. Well, it's kind of on this subject, and it's going to come back up for us again in another discussion, in another example. Yes, we definitely can, Ashley. Let me go off on this little side tangent for 1 second, and we're going to come back to that. In part 3, where it asks what direction the mass is moving, and we talked about if velocity is positive, it's moving to the right. If velocity is negative, it's moving to the left. I want to mention real quick here that there's a difference between velocity and speed. Okay. Speed is actually the absolute value of velocity. Okay, so if we take the absolute value of velocity, we get speed. So realize that there's no direction with speed. If they ask about direction, we always have to refer back to velocity. Okay, so this also means the following, which is important, that velocity has both speed and direction. Okay, so keep that in mind because that's going to come back up. Let's go back to part 2. Okay, we had a question there. What was your question on that part 2? Sure. Okay, so let's just kind of recap what we did. So, of course. Okay, so we wanted to find the time at which the mass changes direction. So we wanted to decide when our velocity was equal to 0. The reason we're looking for when the velocity equals 0 is because when it's greater than 0, it's moving to the right. When it's less than 0, it's moving to the left. When velocity is 0, it's right in that transition from changing direction. Okay, so we want to figure out when our velocity is equal to 0. So we're going to take that velocity function, v of t equals 6 cosine of t, and set it equal to 0. Now, to get to the next step, I really am dividing by 6 here, but 0 divided by 6 is still just going to give me 0. So now I need to solve cosine of t equals 0. I personally refer back to the graph at this point of cosine, and I know that on the graph of cosine that it passes through 0, that x-axis at pi over 2 and 3 pi over 2, and it would continue to do that because cosine's periodic. You also could think back to your unit circle. If you think about the unit circle at pi over 2 and 3 pi over 2, and 5 pi over 2 and 7 pi over 2, you're going to find that your cosine equals 0. Okay. Another way to think about that is if you wanted to solve this equation algebraically, we could do arc cosine of t equals, hold on, equals arc cosine of 0. So we're trying to figure out that value, arc cosine of 0, and that's actually something you could put into your calculator if this was on a calculator section. Does that help on that in terms of figuring out those t values being at pi over 2, 3 pi over 2, 5 pi over 2? If you start with that first place that cosine equals 0 at pi over 2, and you see that pattern, the distance from pi over 2 to 3 pi over 2 is pi. So every pi, we're going to find that this adds on. So that's how we're able to get those other multiples where we get pi over 2 plus n pi. Okay. Good. Awesome. Excellent. I'm glad that helped, Ashley. All right, here's our next one. This time we have the acceleration function in meters per second squared. So we're starting with acceleration. For a particle moving along a line is a of t equals 2t plus 2. And the initial velocity v of 0 equals negative 15 meters per second. For time 0 is less than or equal to t is less than or equal to 4. And we want to find the velocity at time t and the distance traveled during the given time interval. So we've got a little bit of a two-parter here. First, we just need to find the velocity, and then we need to find that distance traveled. So let's start with finding the velocity. If I know acceleration, am I going to differentiate or integrate to get to velocity? I've got to integrate this time. So I'm going to take the integral of 2t plus 2 to get my velocity. And that's going to give me 2t squared over 2 plus 2t plus a constant. Okay. I can simplify here to get t squared plus 2t plus c. And keep in mind that this is my velocity equation because I was integrating my acceleration. Okay, so I've got my velocity at time t. That's the first part they asked me. Okay, I still need to find that c value though, so let's make sure that we finish that part off. Okay, it tells me that I have initial velocity v of 0 equals negative 15, so I'm going to plug in 0 and set v of 0 equal to negative 15 to solve for my constant. So v of 0 will equal 0 squared plus 2 times 0 plus c, and that's going to equal negative 15. So 0 squared is 0, 2 times 0 is 0, so we're going to find out that our constant is negative 15. So now we truly have our velocity equation as a function of time. It's going to equal t squared plus 2t minus 15. That's that final velocity equation we want. Okay. Now, we need to find, at this point, the distance traveled during this given time interval. So this given time interval they're referring to, they tell us, is 4 from 0 to 4 seconds. Now, notice that it says distance, not displacement. Remember that distance is always positive. So we're going to have to make sure that we use the absolute value here when we integrate, okay? So for us to find the distance traveled, when you integrate a rate of stuff, you get an amount of stuff. That's pretty generic in saying that. But we need to integrate our velocity, our rate, to get that amount, that distance traveled. But we're going to have to make sure that we use the absolute value. So we are going to need the integral of the absolute value of t squared plus 2t minus 15. And it specifically tells me that I am doing this on the interval from t equals 0 to t equals 4. Okay. Now, here's the deal. Because this is absolute value, I'm actually going to break this down into 2 parts. Remember that every absolute value function can actually be written as a piecewise function. So I need to determine when is this velocity function, t squared plus 2t minus 15, positive, and when is it negative? So let's do a little side work over here, okay? I can actually factor t squared plus 2t minus 15, and I would get t plus 5 times t minus 3. Okay, and I want to set this equal to 0 because I'm trying to figure out when is my velocity positive and when is my velocity negative, so I can break down this absolute value. This is going to give me t equals negative 5 and t equals 3. Now, if we think about my velocity, I'm going to label that v of t on a number line. It tells me that I'm specifically looking between 0 and 4. That means in this particular situation, I'm basically going to ignore that t equals negative 5 because it does not fall in that interval of 0 to 4. But I am going to make sure that I put 3 on there. Okay. And now let's test numbers in each interval to determine when it's positive and when it's negative. If we were to plug in, let's say 1 into our velocity function, we would find out that v of 1 is negative. And if we were to plug in a number between 3 and 4, we would find out that our velocity function is positive. Okay. So the reason that this is important is because now, since I want my distance traveled, I want everything to be positive because distance is always positive. When I integrate from 0 to 3, because my velocity is negative, I need to put a negative in front of that integral because a negative times a negative is going to make it a positive. When I integrate from 3 to 4, I'm going to leave that piece positive. Okay, so this is going to look like the following. I'm going to have the integral from t equals 0 to t equals 3. And I'm going to have a negative in front of that integral. And I'm going to have t squared plus 2t minus 15 dt. And then I'm going to set up the integral from t equals 3 to t equals 4 of t squared plus 2t minus 15 dt. So I broke down this absolute value into 2 separate pieces to account for where it was positive and where it was negative because I have to ensure that my distance gives me a positive value. Any questions just on this setup or how I broke this down? The number part. What do you mean by that? How I got the -5 and 3? The number line part. Okay. So going back, if we look at t squared plus 2t minus 15, that's my velocity function. And I know that I'm trying to find distance, and distance is always positive. I have to make sure that I account for when that function is positive and when that function is negative. I want it to all be positive because I'm trying to find distance, okay? So what I did is I set t squared plus 2t minus 15 equal to 0 so that I could make a number line for it. But I actually went ahead and factored it. So I factored into t plus 5 and t minus 3. In doing so, when I solve that, I get -5 and 3. I normally would put both of those numbers on my number line, but because it specifically tells me in this problem that I'm only looking from 0 to 4, I'm going to put 0 and 4 as the endpoints, and I'm just going to put 3 on my number line because -5 is outside of that 0 to 4. Okay. Now, I want to figure out when is my velocity positive and when is my velocity negative. Okay, so for example, we might plug in 2 in this first interval. So if I found out what v of 2 was, I would have 2 squared plus 2 times 2 minus 15. So 4 plus 4 is 8, but 8 minus 15 is going to give me a negative. So my velocity from 0 to 3 gives me a negative value. Okay. Now I need to do the same thing for some number between 3 and 4. So we can maybe plug in 3.5. When I plug in 3.5 to my velocity, I'm going to find out that it's positive. The reason this number line is helpful is because we want to break this down into 2 parts. We want to break it down into 0 and 3, and we want to break it down from 3 to 4. From 0 to 3, velocity is negative. So I have to put a negative in the front of that integral. Let me get that pen. There we go. And then from 3 to 4, my velocity is positive, so I'm going to leave that piece of my integral positive. Does that help explain that some? Awesome. Good, good, good. All right, now we got to integrate. So let's see what we come up with. We are going to have negative t cubed over 3 minus 2t squared over 2, which I can simplify to just t squared. And we are going to have a plus 15t. Now realize that as I did that integration, I distributed that negative through as well. Okay, and this is going to be evaluated from 0 to 3. And then in the second integral, I'm going to have t cubed over 3, 2t squared over 2, which I know is going to simplify to a t squared, and then minus 15t, and I'm going to evaluate that from 3 to 4. Okay. And now at this point, we need to plug in each of those bounds. So we are going to plug in 3, and then plug in 0, subtract the 2. We're going to plug in 4, we're going to plug in 3, and we're going to subtract the 2. So we're going to have a negative 3 cubed over 3 minus 3 squared plus 15 times 0 Nope, I got ahead of myself. There should be a 3 there. And then when I plug in 0, what's going to happen to each of those terms when I plug in 0? I'm going to get 0 cubed over 0 minus 0 squared plus 15 times 0. So all that's going to 0. So remember that when I evaluate with those bounds, I'm always going to do the top bound minus the bottom bound. Now I need to do the same thing for my second integral. So I'm going to have 4 cubed over 3 plus 4 squared minus 15 times 4 minus, I'm going to run down to the next line, 3 cubed over 3 plus 3 squared minus 15 times 3. Okay. Any questions on how I did that integration and plugged in before we finish simplifying it? No? Okay, so keep in mind that 3 cubed is going to give me 27, and 27 over 3 is actually going to give me a, 9 in that first term? So it's going to be a negative 9. So in my first set of parentheses or brackets, braces, I've got negative 9 minus 9 plus 45 minus 0, so we can not worry about that one. And then I have plus 4 cubed is going to give me 64 over 3 plus 16 minus 60 minus 27 over 3 is going to give me a 9 again. Plus 9 minus 45. I'm running out of room and trying to squeeze things in there down at the bottom. Let me make us some room up top here. I'm going to jump up to the top here. So at this point, if I look in my first set of brackets here, negative 9 minus 9 plus 45, we are going to end up with 27. And then I'm going to have plus my 64 over 3. Let's leave it as is for right now. And then 16 minus 60 is going to give me a minus 44. And now inside that last set of brackets, right here, I'm looking at 9 plus 9 minus 45. I'm going to end up with a negative 27, but I'm subtracting a negative 27, which is going to get me back to a positive 27. Now, don't be afraid of doing this out by hand. If you've got a calculator in this section, though, you certainly could use it. Let's see what this gives us at this point. We would end up with 27 plus 27 minus 44 would give me a 10 plus 64 over 3. So we're really looking at 30 over 3 plus 64 over 3, which would give me a 94 over 3. And remember, this is distance. So my distance traveled would be in meters. So big takeaway from this is that in order for us to get distance, we have to account for when velocity is negative and when it's positive, because distance always refers to a positive amount. If it just asked for displacement, we would have just integrated velocity and not thought twice about it. But because it's distance, we have to make sure we account for that. Okay. Any other questions on this one? Our work got a little squished down there in the corner towards the end there. Were you able to follow it? You're good? Awesome. Okay, we got one last problem, but first I want to have a little side discussion, a little bit more on speed. Okay. We mentioned that speed was the absolute value of velocity. Okay, so let's make a little note of that. Okay. I want to kind of think through this, okay? Because the next question is going to ask me about when is speed increasing and when is speed decreasing. So if you kind of envision, picture a car that's driving along a road, it's moving forward, so we're going to call forward our positive direction, which means its velocity is positive, okay? If you step on that gas, the acceleration pulls you in the direction you're moving and your speed increases. So in this situation, if my velocity, I need the eraser, here we go. If the velocity is positive and my acceleration is positive, that means that my speed is increasing. Okay. Now you decide, okay, I'm going a little too fast. Let's put the brakes on. So now you're accelerating in the opposite direction or decelerating. Okay, but you're still moving forward, just slower. So now your speed decreases. So this tells us that if my velocity is positive, but my acceleration is negative, then my speed is going to decrease. Now you stop and you shift into reverse. So now you start moving backwards with a negative velocity. Okay. I push the gas to accelerate, but remember we're in reverse, so we're accelerating in the negative direction, so my speed is going to increase. So if my velocity is negative and my acceleration is positive, that means that my speed is going to increase. You put those brakes on again, you're accelerating in the positive direction, so your speed decreases. Excuse me. So my velocity is less than 0 and my acceleration is less than 0. Nope, I got that backwards. My acceleration is greater than 0. We're accelerating in the positive direction. Okay, so take a peek at what we just kind of worked through. Notice that in my first scenario, my velocity was positive and my acceleration was positive. So my velocity and acceleration had the same sign and my speed was increasing. Down below, I got my second scenario, my signs in the wrong direction. Down below, when we were in reverse, so my velocity was negative and I'm accelerating in the negative direction. My velocity is negative, my acceleration is negative. They both have the same sign. My speed is increasing. In my other two scenarios where my speed was decreasing, my velocity and acceleration had different signs. Okay, so here's kind of where we can put it all together and summarize it. Speed is increasing when velocity and acceleration have the same, that should not say speed, it should say sign. Have the same sign. And speed is decreasing when velocity and acceleration have different signs. Okay, so this is a big point to make sure that you know. Okay. Any questions about that relationship before we look at the very last problem that uses that? No? All right, here we go. Last problem. This says that a particle moves along the x-axis so that its velocity at time t is given by v of t equals t squared minus 8t plus 15. Find the acceleration of the particle at time t equals 2. And is the particle speed increasing, decreasing, or neither at time t equals 2? So two-parter. First, we got to find our acceleration, and then we've got to decide if its speed's increasing, decreasing, or neither. All right, so to get from velocity to acceleration, we've got to take a quick derivative. So v prime of t is going to equal a of t, which is just going to give us 2t minus 8. Okay, so there's our acceleration. And now we need to decide if the particle speed is increasing, decreasing, or neither. So we have to determine if the signs of my velocity at time equals 2 and my acceleration at times t equals 2 are the same or different. So let's figure out v of 2 first. We've got 2 squared minus 8 times 2 plus 15. When I do this, I'm going to get 4 minus 16 plus 15, which is going to give me 3. Now let's do a of 2. That's going to give me 2 times 2 minus 8. 4 minus 8 is going to give me a negative 4. So I find here that my velocity at 2 is greater than 0. It's 3, it's positive. And my acceleration at 2 is less than 0, it's negative. Because my velocity and acceleration have different signs, is my speed increasing, decreasing, or neither? What do you think? So you said neither at first, but I think you're reconsidering it now. So if velocity and acceleration have different signs, think back to that conversation we just had. So my speed is going to be decreasing, exactly. Speed is decreasing at time t equals 2 seconds. Because velocity and acceleration have different signs. So if you're not confident or don't really know that relationship yet between acceleration and velocity in relationship to when speed is increasing and decreasing, that's definitely a good one to know for the AP exam. Okay. Any other questions you have for me? That was the last example I had there. No? All right. So next week's stream, I believe, is scheduled for Monday, March 9th at 9 p.m. again. And they are going to be looking at separable differential equations. So hopefully you can join us again, and just make sure that you keep following Fiveable at Think Fiveable on Twitter, Instagram, and YouTube. Have an awesome evening, and thanks for joining me tonight. You are very welcome. Have a great evening.